Hi everyone, Dr. Tom McNamara here, back again for our course in college algebra. We are going to continue our work with systems of equations. And in this video we are going to amp things up a little bit and tackle some 3x3 systems. In our recent videos we have been working on 2x2 systems. And when I say 2x2, I mean 2 equations, 2 unknowns. And 3x3 would mean 3 equations, 3 unknowns. So the key ideas that I need you to learn from this video are how to use back substitution to solve a system. Now, back substitution only works when the system is in a special form. So the next thing we'll talk about is using the method of elimination, which we practiced on a little bit with 2x2 systems, using the method of elimination to get systems set up to do back substitution. So let's jump into an example here. So what we want to do is we want to solve this system of equations. So we'll make it x minus y plus 2z equals 6, 3y minus 6z equals negative 15, and the last equation will be z equals 2. All right, so 3 equations, 3 unknowns, x, y, and z. This will be considered solved when we have values for all 3 variables that satisfy all 3 equations simultaneously. Now, the good thing about the system like it is here is the last equation is already solved. So what we can do is we can take that value and go up to the second equation. So the second equation becomes 3y minus 12, right? If z equals 2, then 6z equals 12 equals negative 15. And I think this works out to be y equals negative 1. Let's check it out here, right? To get y by itself, I would add 12 to both sides, giving me a negative 3 on the right-hand side. 3y equals negative 3 implies y equals 1. So now I have the value of z, and I have the value of y. I take both of those and go up to the first equation and substitute those in. Now this is an equation that involves only x, only one unknown quantity, so I can solve it. Let me see here. I think this works out to be x equals 3, right? Because minus negative 1, that's actually a plus 1, right? So that's plus 1, oh, no. Plus 1 plus 4. So this is actually a 5. I have to subtract. So it looks like x is actually equal to 1. Okay. So my solution is 1, comma, negative 1, comma, 2. And remember, whenever you solve an equation or a set of equations, you can always check your work by plugging those in. If I plug in 2 for z, this becomes 2 equals 2. That's a true statement. If I plug in y equals negative 1 and z equals 2, this is negative 3 minus 12. Negative 3 minus 12 does equal negative 15, so it also works there. If I plug in a 1 and a negative 1 and a 2, this is 1 minus negative 1, which is plus 1. So 1 plus 1 is 2, plus 4 does equal 6. Those values of x, y, and z work in all 3 of the equations. Now, the important thing about this system, the thing that let me use back substitution, was that this last equation involved only one variable, and then this involved only 2 variables. If this involved all 3, then I'd be stuck, because if I plug in the value for z, well, y and x are still unknown, so I can't solve. So to do back substitution, your system has to look like this. First equation involves all 3 variables. then 2, and then finally just 1. It has to look in, I often call this triangular form. So your system has to look like this for you to be able to do the back substitution process. So let's take a system that doesn't look like this and we'll turn it into a system that does look like this. All right, so x plus y minus 2z equals minus 3. Second equation, 2x minus y minus 3z equals negative 9. And lastly, negative y plus x. What? I really want that? Yeah, sorry. Negative x plus y plus 4z equals 13. Okay. So, this is not in that nice triangular form set up for back substitution. So I'm going to need to do eliminations so that I get an equivalent system that is set up for back substitution. So my first target is this x. I don't want equation 2 to have an x. I want to eliminate the x. So what I'll do is I'll take negative 2 times equation 1, and I will combine that with equation 2, and this will be my new equation 2. Okay, that's my new equation 2. So let me do that here. So negative 2 equation 1 becomes negative 2x, negative 2y, plus 4z equals 6. Okay, remember, every term has to get multiplied by negative 2. So this becomes negative 2x, negative 2y, positive 4z, right, 2 negatives, and then positive 6 on the other side. And then over here, 2x minus y minus 3z equals negative 9. Those cancel. Negative 3y plus z equals negative 3. Okay, so this is my new equation 2. My new second equation. All right. Now, my next target, right there. I don't want equation 3 to have an x either. So what I'll do there is I'll just take equation 1 plus equation 3. Okay, notice in my first 2 eliminations, I played equation 1 against these guys to get rid of the x's. Okay? And remember, when you're doing eliminations, you gotta pick what you're gonna eliminate. So I decided with this first elimination, I want to get rid of that x. I don't want that to be there anymore. So I'm looking at this coefficient up here. I'm seeing this has x, this has 2x. I want these guys to match up but have opposite signs. So I hit that with a negative 2. That's why I chose that multiplier of negative 2 right there. Now here, equation 1, equation 3, well, they already have opposite signs, so that's why I don't have multipliers in this case. Okay, so those cancel. This becomes 2y plus 2z equals 10. 2y plus 2z equals 10. You might notice here everything is divisible by 2, so that's the same as y plus z equals 5. Okay, now this is my new equation 3. Okay. Now, I don't normally rewrite the system, but since this is our first time doing the eliminations and everything, I'm going to write it down. Okay, so my new system looks like this. Equation 1 has stayed the same. That's equation 1. It still has x, y, and z. Here's my new equation 2. Negative 3y plus z equals negative 3. And this is my equation 3. Okay, so notice I'm closer to the setup I want. Remember, that's a triangular system where the first equation has 3 variables, the second has just 2, the last equation has just 1. That's what I want. I'm close. I just need to get rid of that y. So I'm going to do one more elimination. Now, if I use equation 1 again, that would be a mistake. Because if I tried to eliminate the y using equation 1, I would bring back x. I don't want to bring back x, I just eliminated x from the third equation. So now I'm going to play equation 2 and 3 against each other. All right, so my next elimination is going to look like this. Okay, it's going to be equation 2 plus 3 equation 3. So equation 2, remember we're using the new equation 2. This is now equation 2. Now 3 equation 3. So 3y plus 3z equals 15. Cancels. 4z equals 12. And of course that implies z equals 3. So, now that gives me a new equation 3. So my new system is x plus y minus 2z equals negative 3, negative 3y plus z equals negative 3, and finally z equals 3. All right. Good thing about this, got that nice triangular form, which means we are ready to do a back substitution. Okay, when you have a 3 by 3 system, you will need a maximum of 3 eliminations to solve this system. If you find yourself having to do more, something's gone wrong. You've made some kind of mistake. And I would also note that when I'm solving a 3 by 3 system, I like to be very systematic. I solve it the same way every time. Eliminate this. Eliminate x from equation 2. Eliminate x from equation 3. And then use the new equation 2 and 3 to eliminate y from equation 3. So now we got this. Okay? So we can take this and go back up the chain, figuring out the values of y and then finally x. So remember, this is now our system. So z equals 3. We bring that up to the second equation. Negative 3y plus 3 equals negative 3. I get y equals 2. Right? Subtract the 3 over. Negative 3y equals negative 6. That means y equals 2. And then we take both of those known values, the value of y and the value of z, and we go up here. Okay, to equation 1. We know that z is 3, so this becomes negative 6. We know that y is 2, so that becomes a 2. Okay, and it looks like when all is said and done here, I think I get x equals 1. Right, that's a 2, that's a negative 6. So combine those, 2 minus 6 is negative 4. So this is x minus 4. On the left, add over the 4, you get x equals 1. So, I am proposing that the solution to the system is 1, 2, 3. And remember, we can always check. Plug those values into these equations, see if they work. 1 plus 2 minus 6. 1 plus 2 is 3, minus 6 is, in fact, negative 3. 2 minus 2 is 0. Negative 3 times 3 is negative 9. Negative 1 plus 2 is 1. plus 4 times 3 is 12. 1 plus 12 is 13. So those three values for x, y, and z work in all of the equations simultaneously. That's what we wanted. Okay, so we have solved a 3 by 3 system. So the process is we start with something like this. We do 3 eliminations to get something like this, where we have 3 unknowns, 2 unknowns, 1 unknown. We want 3, 2, 1. Once we have the system like this, back substitute, and you get the values for x, y, and z that work in all three equations at the same time.